Okay, 6 o'clock. Hope everyone's feeling really good. 6 o'clock on a Tuesday, week 5. It's kind of racing away. So this is your second last lecture with me, which is kind of surprising and a little bit sad for me. I really like doing these things. I appreciate all you coming, and I really enjoy getting the opportunity to do this. It's a good thing for me. It's completely selfish. So, yeah. So, what would I want to say? Okay, cool. We started really quickly. We finished off the last section, sorting. We did sorting to death. Kind of sick of sorting, but idea is just thinking about computational complexity. I did a little bit of mucking around with some boring stuff of just like, files, like everything in computing is just a collection of bytes. It's just like you have to pass it through some program to interpret it. Talk about like, if you're going to go out and do stuff in the real world, it's like the bane of every data scientist's life is CSV files. It's like tabular data is the thing. Like, so we'll talk a little bit about CSV. There's not much to say. It's kind of boring. But, and JSON, this one kind of wanted to go a little bit off track and talk about HTTP requests a little bit more, because it's like there's JSON as a file format. Probably help you with the homework if you've seen it, just a little bit of like RESTful style stuff. I'll talk a bit about that later too. And hopefully we'll get into floating point this lecture, because we're going to run out of time if we don't. Okay, cool. So not much to say about comma separated variables. It's like everyone, I guess, kind of interesting. I think like, what's the most ubiquitous programming language? What does anyone want to guess? What's the one most people can program in?
No, sorry.
I think it's Python. What do you think? Excel. It's like, it sucks in so many ways, but everyone can use it and they can see the data, and it's like a really good way to interact with data. Had a little bit of a chat about this. Didn't start this up. Cool, Control Shift plus. Got data frames. What did we say in this example? Data frames using CSV. Didn't install that. But there's another one that's like a more cut down version of this, is like, you can have all this machinery. Sometimes you don't want that much machinery. This thing has nice access to functions and stuff with CSV. I'll show you that, but I'll also show you another like more brain dead way of reading these files. Let's wait for that to go. So we're going to set up a data frame. So I think I showed you there's lots of different ways you can do these constructors for data frames. It's like, don't actually like this equals one where you say names equals an array. That's okay. If you go look at, I recommend, like, this has probably come up for people already, but if you look at the documentation for data frames, Julia, docs, documentation will come up. You'll see a bunch of stuff about wrangling with data frames, cheat sheet. This is the kind of stuff you want to see. Blah, blah, blah. Go off and look on the internet. Anyway, documentation is pretty good. There'll be a quick start thing. Tabular data, it's like the way everyone thinks about it is like things laid out like a matrix. We've got a little one here that's just like names, ages, and gender. Have I shown you this one, this colon before a thing? Has that come up yet or not really? Kind of, maybe.
In homework, it comes up as plotting something in block. So
yeah. Yeah, this is if you want to create something. If I go A, oh, that's useless if I do that. If I go type of A, it's a symbol, which is like reasons. It's not a string, but you can think of it like a string. But it's like, if you want to set up variables, they'll all be a type symbol. But yeah, just a different thing. Like these things in the data frame, it's often like you have these problems of like, I want to construct a data frame name and I want some funky punctuation in there. Constructing it as a symbol is usually the way to go if you want to put it in. But anyway, data frames will support all these useful things where we've got like, this is a question mark symbol because it can have a missing value. This is like really useful when you're in your types. Like you've always got this problem when you're dealing with tabular data. Anyone who's done statistics knows this. Is like, I get this one in my day job and I hate it. It's like, there'll be a missing column in a CSV, like a missing element in a CSV. And you go like, does that mean 0 or does it mean missing or does it mean nan? Because they're all kind of different things. And, should I be imputing what the missing value is or should I be treating it like 0? That's like all the bloody time. Very frustrating. So Julia's data frames will support missing fields. That's great. There's a missing type. Type of missing is a missing. You've also got a nothing because, you know, they're different things. Useful things to know about. Cool. What are we doing? So if we have a data frame, we can write this thing out with this CSV. It's got this method write. CSV, we're going to write out to this file named people as a data frame. People, if I go look on my computer now, how do we want to do this? What do I call it? People? Is that right? That's people CSV. So if I open that code, hide. Okay, so this thing is just a text file with this, the CSV is comma separated variables. So it's put a comma in and a new line at the end. So you know where you are in rows and columns in this thing. Much more general than this, like there's no reason to necessarily have, you know, nothing special about commas, and sometimes they're not useful. Like you've got this problem if your fields, oh, can't spell. Using delimited files. So sometimes you might not want a comma for some reason, like say it's a string and it's actually got commas in it, then you don't want commas because you'll get really confused. You can actually have all different sorts of things. So you can, there's this lightweight one if you don't want to mess around with data frames and stuff. I'll just get that one. This is like a much, much smaller library for just dealing with delimited files. Just go to the documentation. So the method for this guy is read DLM source, and it gives you a delimited, which you have given as a char. So this guy, I go read DLM people.csv. And tricky one is that it's a character, not a string for this guy. Should be able to read that back in as a matrix, much smaller, lightweight thing. Doesn't come as a data frame, just comes in as a plain array. But if I want to, you've got the opposite one, like if you want to write DLM, you want to give it like say tabs instead of spaces, then if I go back to this VS Code one, oh, way to go. Oh, I didn't put that. Yeah. Yeah, I have to actually do that, right? Didn't write, got to read it. Read DLM into something. Yeah. I'm glad you're on the ball. Ah, didn't work. What's that? Oh, it's tab. Because it's, geez. CSV, I'm in a state here. Write it, then I'll read it, then it will actually have something in it. And if I write it again as a delimited file tab, hopefully this time, big reveal. Hey, I'm only a partial idiot. Thank you for helping. Cool. So this is with tabs instead of spaces, because you might like more generally, whatever, the special delimited character, CSVs just seem to be the one that everyone's used. Not much to say about that. Excel's a curse. But again, it's popular, so you got to deal with it. I don't know if you want to see. So, just examples of mucking around with data frames here. This will come up again. I don't know how much we want to say about this because data frames are kind of like you'll cover this again, but there's some examples here of mucking around with data frames. You read it into sorry, I probably do want to say how you'd read it in because I just did that right one. So csv.read, that's me doing something random in the past. People, you have to give it a sync when you read this in with the CSV library. So you give it a data frame. Data frame? Should be data frame. Yeah, so that's the symmetric method for the CSV one. So you can read them, write them, muck around with data frames. Really common. I hate CSVs. I wish they'd go away, but they never will. on the same topic is JSON. Does anyone had a poke around with JSON yet? Have they had to have a fight with it? Do you like it? Not particularly. So this is there's a saying in computing about worse is better. And it's usually like the idea is like if you have a good thing, but it's really slow, two things that go together is like worse is better and perfect is the enemy of good. They're two kind of things you have to think about all the time. JSON is completely an example of worse is better, where there's like been all these different standards for like, we go like, I've talked to you a little bit about data types. So I've shown you some structs and I've shown you like dictionaries, and you go like, oh, cool. They're kind of dictionaries are kind of flexible, but they're a little bit too flexible. So like, you kind of want this idea of a schema, like what's the layout of this dictionary? So if I'm going to read it in, how do I get the data out of it? Has anyone had that in the homework where you're poking around in the IPython notebook when you load that in and you go like, what's in there? I've got to kind of navigate this thing and it's disgusting. Does that come up for anyone? It will. Like, they're kind of like a dictionary is really free, but it's a little bit too free. And the documentation of the layout is kind of like never kept with the thing. So there's been all these ideas through history about like, you know, it'd be really good if we did this thing. So there's all these things like XML and stuff. And then in the end, just like this idea of just like, just a dictionary as a string, it'll be fine, is what everyone uses now. This is JSON. It's kind of like the most popular data format on the internet. So there's kind of like two things I want to talk about here. Came up after the last lecture, so I thought I should talk a little bit more about it, but I'm not going to go not going to go deeply into it, just like a tiny, tiny superficial thing on it. Most things are talking via the internet protocol, HTTP. And there's kind of like, you'll hear this idea of REST APIs, and it's kind of funny because most programmers, if I poll them, I did it today with someone I work with, just to be mean, don't actually know what it means. So it's like, it's an overloaded term, and there's a whole thing. I would encourage you to go off and read up about it anyway, because it'll come up if you ever do more programming. There's the idea of a REST API. Wikipedia wins, I think. Bugger off those guys. Someone actually did the history comes from this guy, Roy Fielding, in 2000. He did a PhD thesis on it. It's like, what's the ideal architecture for the internet? And he had this idea of things talking via HTTP and special structure of the architecture about it being stateless and all these other wonderful things. Too confusing. So they talk about RESTful now, wherein it's just like, yeah, you just use HTTP methods. So that's kind of where everything landed. And basically the whole internet is people slinging JSON back and forth through HTTP requests. Like, does anyone, so this one will come up, like, I hope everyone, you learn a bit more. When you start to do this course, these sorts of courses, you start to think about how the sausage is made, like all the things you have, like a web browser, you can go like, I hope everyone is aware of it. If you do Control-Shift-C, you can start to see, oh, there's an inspector and I can go over these things and see what they are. And there's a console here that's like a terminal and I can see all this stuff. Is anyone aware of this stuff? Anyone used it? Good or bad? Usually bad, but anyway. Yeah, so there's like, yeah, that's a whole thing. Usual data format you'll get though back is JSON. So I think it's interesting. I wanted to show you this is like GitHub has a public API. And most browsers will support JSON coming through. So like current user URL, GitHub user. This is like a view of the JSON you'd get back if you just hit this thing, but we can do it programmatically in Julia. You can do it in all modern languages. Has anyone mucked around with requests and stuff in Python? A few people? Recommend looking through a few different languages to see how they do it. The Julia one, HTTP, is basically like with equivalent in Python would be this requests import you'd do, request library. What I've done here is just a simple example of a HTTP request. So there's a whole bunch of these. Go down. Yeah, that's what I wanted to do. It's a whole bunch of request methods you would do. You've got like, most common two, though, would be get and post. So like, just get something from an address with this optional payload. post is like you're going to give it something and expect something back. So like when you're doing the llama one, I imagine if you're driving it from Julia, has anyone started doing it yet? Did you do it with a post or, yep. You think so? Yeah. So that you did it a while ago. Yeah. So you do something like that. Cool. So yeah, I've just shown you a quick example of a get request here. So I've gone to this GitHub API. So api.github.com users, that's me, and repos. So if you wanted to do a web request, we did this before with the Shakespeare one, but we went to some random MIT thing and got Project Gutenberg for Shakespeare. Most websites will have public APIs. Sometimes they'll have authentication. You've got to pay, which is kind of bad, but makes sense. Someone has to make money somehow. Encourage you to play around with this stuff. So this one, you can see we've got a bunch of stuff. Web request. All the code in the notes is lazy, but again, we talked about this before. You want to check the status 200, that you actually got what you expected. And the body of this thing is in this JSON format. So when you parse this JSON format, when you parse this request body, you're going to turn it into a string, and then you go, well, actually, this is JSON formatted string. So JSON formatted string, these will come through into Julia as dictionaries. So let's do it without. So if I just get this as a string, this might be disgusting and I'll regret my choices. But if we don't parse it as a string, you'll see that we get these little funny symbols. There's a square bracket, which will mean it's an array. And then curly bracket means it's a dictionary, start of a dictionary. You probably want some nice formatting of this. I don't know if I added a JSON parser. Most browsers, so this would be an example of where you want to add. I have no idea if this is a good one or not, but I'm just going to install it. And we'll see format document. Oh, it's probably a bit long. So it's having trouble.
All the backslashes are messing up all the string escapes.
Ah, yeah. Yeah. Anyway, blah, blah, blah. We won't worry about it too much. But yeah, so this thing, I guess basically this format is, for JSON formatted strings, you'll have something like this. You'll have a key, like name, and then the equivalent thing would be Paul. So as a JSON string, this would be like the equivalent in Julia would be doing something like dict name goes to Paul. Yeah. Anyway, blah, blah, blah. So we got the web request, we did web data. So this is the thing I was going to say is like JSON's super flexible because it's like a dictionary. You can just think of it as like a dictionary. Down at the little leaf nodes of the dictionary, if you can think of like the final values, you've got some base data type that will either be like a number, a string, a Boolean, or a date. And then you get arrays and dictionaries of those things all the way up. The numbers aren't quite numbers though. So there's some funny things like when we go to talk about floating point, there's no special values for inf and nan. They're not supposed to be part of the JSON spec, but not every JSON library is a nice JSON library and does the right thing. Sometimes I think the Python one will actually let you write infs into JSON. So it's not actually valid JSON. So you got to be a little bit careful, but you always have this game of like, oh, I got something back. What is it? So you're going to go like type of web data. Oh, it's a vector of type any. So then I can go like, well, cool. If I get the first thing, what is it? It's a dictionary of string any. And then you go, cool. This is the kind of game you get to play, keys. And then you go, oh, there's all this much stuff. So yeah, the lack of schema is a little bit annoying. But again, a simple example, if we do a list comprehension of this guy, we're listing my repos on GitHub, which is a pathetic 6. And I just got these two fields exist in these bottom ones. So there's some things you could say. So it's got a name and a language. And I did this comprehension for R and web data. So there's displays, monkres, blah, 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 blah. Cool. Basically dictionaries. That's the way. Map it in your mind. I think that's fine. Any questions on that? No? Happy? Move on. Overdone. Okay, this next little bit I'm going to rush through. I think I would point you to this as like a reference for doing plots. Like if you want some examples of plots, it can be a little bit hard. The Julia documentation is kind of weak. I think I've said this before, that in all our notes, I've said, you know, we're kind of using plots, but I think everyone's moving over to this guy. I don't know if it's actually pronounced Makey or it's Makie. Like it's meant, I think it's from the Japanese word. So whatever that pronunciation would be, you can do pretty plots in Julia in this library as well. Kind of up to you, what you use. Best off to move with the times, I guess. This will, plots and Makey will have a library of like magic spells that you'll want to look through. So I nearly always go to the demos folder for these ones. There'll be like a gallery of like, you know, if you want to do this, what's the source code for it? It'll have it here. So blah, blah, blah. There's lots of different backends. So plots is just a front end to lots of different backends. Like this is a whole thing of like making images on a computer is not fun to deal with window resizing and how you draw to the screen. It's a whole big thing. It's a better story than it used to be, though. I think for pretty ones, I'd be going for this one these days, though. So we've just showed you some basic stuff. You've got some nice, useful constructors, like if you plot sine and cos, it will do a little bit of data automatically for you. Typically, you want to put labels in. More examples are like pretty things you want to do if you want to plot a surface or a heat map. These are the kind of things where I think the API, so if I say that, we just talked about APIs, it's like the interface to plots, the programming interface is kind of gross. Like there's too many options and they're hard to discover. So you end up kind of just looking for a list of magic spells to learn how to drive it. But I don't think that's, I think it would be unfair criticism of just this plotting library because they're all like it. Cool. Yeah, more plots, more plots. I don't think there's much to say. You end up having a nightmare with things like, I'd say this one, like I'd be very unhappy if I made that plot because it's like they're all running over each other. So you'll go like, I just want to rotate the ticks so that they're not over each other. And then you have a fight for a week and trying to get it right. That's a normal story. I do like this one though. And I think this will come up for question 15 or 16. It will ask you to make an animation. Is that true or am I lying to you? Not there yet, but this one's kind of cool because you can anim, wherever this guy is. There's macros for this as well. I don't think you have to do it this way. There's probably better ways to do this or different ways to do this. This might be a little bit more annoying, but this will capture frames. So like if you plot in a loop, you've got this anim constructor, and then every time you add this frame method to anim, and then you can make like GIFs and stuff at the end. So to do cool things like this. This is like, when I started first using Julia, I kept this as like a historical artifact because I wanted to see, I started using Julia in 0.3. So before it was 1.0, that's about when I started using it. And I kind of like go like, I think I said this a while ago, but like if you want to learn how to program, coming up with something you're interested in and then trying to do a little application is a really good way to learn. Lots of people really, really like computer graphics and things like that. So trying to make cool plots. I'm not so into the graphics because my aesthetic sense is pretty poor, but I do like mucking around with maths. So I think this was one of the first things I made when I started doing Julia. I did a simulation of a wave equation, like drops in a wave equation. And I didn't have any of these nice macros that you guys get. So I had to actually write each one of these frames to disk and then use a program called FFmpeg to turn it into a video. Yeah, it was horrible, but this was like I kept this one because this is like my demo of like trying to see how things worked in Julia. So just like practice what you preach. It's like, this is what I do when I want to learn a language. I'll give myself a little toy problem, like going like, I want to solve the wave equation, do a numerical method. make a thing that kind of looks pretty. Maybe it doesn't look pretty, but maybe someone with better aesthetic sense could make it look prettier. But I think I just wanted to say that because it's like you're in a much better situation now because you've got this nice little macro to make a GIF. You don't have to do any of that horrible work. Cool. Plotting and statistical summaries. Like if you're a statistician getting basic statistical summaries, you can do everything you would expect you want to do. So this one's getting some data, temperature data, again from the web. Some stuff about reading from an IO buffer, this string. Don't worry too much about that. Just copy it across. Like basic exploratory data analysis. This is just meant to show you like, you know, we've got some data, we want to muck around with it. You can do all these things. Like this isn't in base, the statistics and stats base, they're taken out of the base, Julia. So you have to import modules if you want to do mean. So for example, I'm going to regret this. I can just do it in a new session. Sorry, I'm not thinking too hard. Control-Shift++. If I try and go x equals 1, 2, 2, 3, 4. If I go mean, okay, I don't know what mean is. So using mean x. So, you know, these are all, the idea is to make base Julia library small. So if you're going to do Julia with, you don't need all the guff, but I'm a mathematician. I sort of want stats and linear algebra as a default, but that's kind of a thing. Stat changed around 0.4. I think they did that, or 0.5 for Julia, where it all came in. But this is basically, again, just like a reference for like all these things you might want to do. Mean, harmonic mean, geometric mean, variance, standard deviation, median, quantiles, interquartile range, and summary stats. Like that's probably the one. You could just do that and it will tell you a bunch of stuff. Yeah, so that all exists. Just as, again, as a little reference, EDA is a big deal. If you're, again, in my day job, that's a thing I have to do once every month or so. I'll get some client data and we've got to muck around with it, doing statistics and correlations and stuff. Okay. Anyway, that's just like show you some stuff, run away. Numerics, let's go to the good stuff. So, okay. I've said floating point, you've seen floating point. I never actually said what it was. We're going to start going into floating point. So I think in that first lecture, you would have seen the C code and it would have said like, you might have seen like, if it's the different floating point types. 64-bit, given the history, there used to be single precision was a float 32, double precision is a float 64-bit. Back in the old days, they thought 32 bits was enough. They were wrong. I always want more accuracy. That's this funny name of double precision. That's this standard IEEE. IEEE is the like electrical engineering mafia, I would say. Yeah, I do a lot of stuff with IEEE, but so they're quite good in some ways, but they control a lot of stuff. So 754 is a standard. So again, how do we represent things on a computer is like, it kind of ends up being this designed by committee and standards of like, we're going to try and have this thing. What we're going to do, what it is meant to be, how do we represent the real numbers on a computer? It's like the real numbers, you know, there's a lot of integers, but there's kind of like a lot of real numbers. So how do you make the whole of the real numbers fit into 64 bits is the question. And it's kind of interesting how it's represented in memory is what we're going to talk about. So there's a little function here, pretty print float. So we've got a type annotation here that it will only work if the type of X is a float 64. So it's probably like bad name. It's like pretty print float 64, not pretty print float, because you'll have the different floating point numbers in Julia. You'll have 16, 32, and 64. This will get the bit string of X, and we're going, the first of the bit strings is the sign. So first deviation from integers, if we had the signed integers, we don't have a signed bit, right? I said, oh, that's like how I would have done it. They do that for floats, so yay, they did something sensible. The significand, exponent is the next from 2 up to 12. And then the significand is these other bits, blah, blah, blah. So we'll just round that for, why not? Doesn't really matter what we do, but. Okay, so sign of this bit is 0. The exponent in binary is blah, 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 blah. And the significand is this blah, 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 blah. If I do minus x, we should see that the sign flips over. Other things kind of the same. Hopefully exactly the same. Cool. So what do I want to say? So this is kind of like just like scientific notation for computers. But like if you go 1 times 10 to the minus 6, it's kind of like that's not a bad mental model for how this is going. So we've got a sign bit. Now we've got pretty print. You've got a sign bit. You've got something like the bit you out the front and something like the exponent you'd raise it to. But if you're going to go for a 32, the single precision, the float 32. So in Julia, this is a float 32. Again, it's just a different amount of precision for the exponent and the significand. So we don't get 64 bits to play with. I wish I could show this on the same screen. So 2 to 12 for this one, 8 to 9, 10 to 32 instead of 13 to 64. So there's lots of stuff going into the significand. So this has consequences for how much resolution you can get for a particular type of float. So what these things are actually talking about though is the way they've chosen to represent it is that there's a sign bit. We've got this little bit in here, F. So it's 1 plus this thing, F. That was that bit when we were doing the pretty print. That's the mantissa, sometimes called the mantissa or significand, and then there's the exponent. So we don't have heaps of bits for the exponent, but we've got lots for the significand is usually the pattern. Slightly weird consequence of this. Yeah, basically this is like powers of, so reciprocal of powers of 2 for this F thing in bits. That's how that's represented. The one is funny. It's like what this is equivalent to is that I think there's all this stuff here. I think I always find it useful to look at this picture, but maybe not this particular picture, but there's kind of a pattern to this that I think is kind of weird. So like if I was coming up with floating point numbers, I would have done something like the log of it. Like it would have been exponentially scaled. If I looked at the gaps between subsequent floating point numbers, if I was doing it, I would have gone for logarithmically spaced. So like, it's not actually what happens is that they're equally spaced between powers of 2 for floating point. That's what they've gone for. I didn't come up with it. Don't blame me. But that's kind of what this pattern, that's what they've gone for. So equally spaced between powers of 2. You don't get all the real numbers, but you'll get like a fixed precision between growing powers of 2. Cool. Yeah, so consequence of this is that we're going to have like, I think I would have shown you this. Floating point EPS is like this thing of like, I think I was thinking when we were doing the roots, I was going like, oh, it got really small. Like it got like to number like 10 to the minus whatever. That's like, for each type of floating point number, there's like, well, I don't expect that I could actually do any better than that in floating point because of this spacing thing. There's always some relative error you kind of have to live with. This is such a useful thing to know that it's built into Julia. You can look at this guy. So EPS, return the machine epsilon of the floating point type T. So default type is float 64. This is defined as the gap between 1 and the next largest value represented by that type. So it tells you like, if you're at 1, what's the next little increment you would get? So I kind of have these tattooed in my brain because I play with this stuff all the time. About 10 to the minus 16 is like float 64. float 32. Anyone want to have a guess what that's going to be about? Sorry? Close, 10^7. And, you know, that one's actually pretty terrible. Like they're actually pretty like the gaps are pretty big by the time you get into float 16, which is like, you know, what they were going for with the design of floating point with reals is like this huge dynamic range. It's like if you're doing to do a simulation of like a galaxy or solar system or something, there's all these different timescales you have to model over. Like you've got a huge dynamic range you have to cover. So you're going to go like, well, this many bits will be good enough. I'm kind of happy to live with this floating point error. So this has kind of disastrous consequences. How you would actually calculate that though is basically just this. It's like when we said, this is in this floating point specification, we said 13 to 64 is how many bits you get in the significand. It's basically like 2 to the minus that is whatever these epsilons are. So that's, you know, that's just shortcut for that. So so the actual numbers you get are, you get 52 for a 64, 23 for a 32, and 10 for a 16-bit float. There's actually weird types of floats that are coming out now. Has anyone come across these? I'd be kind of surprised. All to do with machine learning. You guys are mucking around with an LLM. So there's a huge problem in LLMs that, you know, I don't know what number of parameters they're up to now. They're in the hundreds of billions probably. Actually getting that to fit in memory is like one of the biggest problems. So if you've got a consumer grade GPU, you know, you get like 8 gigabytes of RAM for a reasonable one. Like you can't fit one of those models into RAM on one of those things to do inference on. And if I'd encourage you to play around because you've got the Olama thing. Like if you get one of the big models, try and run it on your CPU and see how long it takes. It's like you think about for somewhere like OpenAI, how much money they're hosing on doing inference for people. It's like, like they would be running inference on a GPU and probably a cluster of GPUs. So that's kind of crazy. They use these things called B floats. A brain floating point. I don't know why they went for that name. It's terrible. But there's like all sorts of exotic small floating point numbers where they're kind of going like, well, you know, we probably don't have the dynamic range, but there's kind of like a range of numbers we care about more in this case. So they'll muck around with the actual representation of these things. Not something I've come across, but yeah, again, yeah, I don't know what I think I've drifted off. So you can think of this as like a relative error. Like relative error you have to live with. So we've got an example of this here. I think it's worth going through this because there's some little bits of syntax we can see. You're all going to be really good at Julia by now. So we're going to do non-squares. So we're going to get the numbers between 1 and 100, and we're going to square them, and we're going to do the set diff of those. So what that should be is like, we're going to take the difference between this set and this is a collection and this is an array. We have a comprehension that's squaring it. So we're going to take out all the numbers like 1 and 4 and 9 and 16 out of this set, because then, you know, they're like cheating because they're too easy to take the square root of. So we're going to give ones where it's like, it's going to have like a proper, you know, decimal expansion when you do the square root. We're going to do this little x bar equals square root, x tilde is going to broadcast square root against these square root numbers as float 32s. So that should be all fine for you. And that, again, that's going to be like numbers between 1 and 10 that aren't the integers when we do that. That's what we're doing there. So what we're going to do here, though, is if we do this not as promoting them, or not as interpreting them as float 32 numbers, we're just going to do them as float 64. The idea here, this is a bit rubbish, but the idea is that float 64s have so much more resolution than float 32. We can kind of see the distribution of errors. So it's like we're using float 64s as like a proxy for like, if it was perfect, this is what the answer is, because we expect the accuracy to be so much higher, given that epsilon for float 64 is like 10 to the minus 16 versus 10 to the minus 7. So if we plot the relative error between these two, we're going to go epsilon equals x tilde divided by x. minus equals 1. And some cool little plot. So we're going to do a scatter plot. Oh, using plots, didn't add it. So again, getting a bunch of like magic spells to see. So what we're going to see here is we get some distribution of errors. This is the errors between square root as float 32, square root as float 64. That's the relative error between these two. And if we put in this plot, this is kind of, I've got another cool little bit of syntax here. We're going to take an anonymous function that x goes to 0.5 times x float 32, x goes to 0.5 float 32. So what this should do, maybe you'll see it, it'll put these black bars on. That's all that was doing. That's actually way harder than it has to be. You can actually do H lines, blah, but that's a way easier way of doing it. If you want to put a number through, say we want to do it at 0. Oh. H line, sorry, I lied. So that's kind of the easier way of doing that. But just so you see a little bit more exotic syntax, we'll put that one in there. So what you can see is that between this floating point epsilon, the errors are kind of bouncing around. Like, okay, this will be a little bit of a philosophical question. It's like, what would you say about the distribution of those errors?
Normal, maybe distribution.
Yeah. So maybe random, but kind of maybe not quite.
Yeah.
There's some structure to this. Like it seems like they're correlated a little bit. Like if you look at the envelope, there's some structure to this. Maybe you have to go over a bigger range. But I kind of want you to think about this because it will come up in the lecture of like, we've done this thing. There's all these magic tricks that we haven't actually talked about is like, oh yeah, you just draw a number from a random distribution. It's like, kind of want to use this as a bit of front loading to go like, how would you actually show that something is random? And how would you actually procedurally generate random numbers? It's like, it's actually quite a statement to think that you can do that. Because like, it's even actually like proof that a distribution of stuff is random is kind of complicated. It's like, it's kind of like an open question. Floating point, we get some distribution of errors. Superficially, you would say they were random. If you wanted to test that they were random, that's not a good idea. Kind of leading into this is like, if you were going to make your own random number generator with a seed, you could use floating point errors. Do you think that's a good idea or a terrible idea? It's a bad idea because like they're too structured. They're too structured. And I always use, this is kind of a joke, but like if there's all these theories about the universe as a simulation, it's like, not in floating points because we actually get randomness that isn't structured. So it's got to be something else if it is. It's my existence proof that it's not a simulation. I think you'd see that in an experiment. But yeah, just wanted to see that with you because this will come up in later sections. You're going to talk about how you would actually generate random numbers on a computer. I think there's a saying by von Neumann that if you think you can generate random numbers by a procedure, you're living in a state of sin because it's kind of like an exotic thing to think you could do this. Even we were talking about dictionaries and hashing, and like I think I talked about hashing in Git. It's like this idea that you could take something deterministically and generate something kind of random in the output. Same thing. Can you actually do that? Is that a thing? Has implications for cryptography, compression, machine learning. They're all kind of the same problem in a way. Cool. There's also some special values for floating points. So if I do bit string, sorry, if I do 0 by 0, that's obviously a nan, but there's actually a special floating point value for nan. I was just saying in JSON there isn't a nan, but in floating point there is. That's one of these things. You also get two special other ones that are really useful when you want a big dynamic range. You've got inf and minus inf. So they have special codes. They go to special spots. Yep.
Just going back to like the random question. Given like quantum computers might be a thing.
Yep.
Maybe sometime in the future, what implications will that have on like, true randomness?
I don't know. It's kind of beyond my pay grade and it's super fascinating. It's like if you're young and excited and go off and learn that stuff, I would say, and then come and tell me in a year or two. It's like, yeah, Yeah, it's like we talk about randomness and we talk about probability distributions. It's like, do true random processes exist? It's like kind of ask a physicist. But more interesting question from my side is like, how would you prove that something is random? I'd say that ties in really closely with these ideas of machine learning and compressibility. Like if you can't compress a representation of a thing, it's probably random. That's this idea of Kolmogorov complexity, if you go into that stuff. Super interesting stuff. Okay, so we get some fun stuff. And this is like, I talked about CSVs as being a pain bum for my day job. This is another one. Certain numbers that you'd hope fit in floating point don't quite fit in floating point. So if I take the big float representation of 0.1, you notice that it starts doing some garbage out here. It's like there's no 0.1 doesn't quite land nicely on a float 64 representation. This unfortunately breaks mathematics. So this should be fine. Everyone, this should be fine, right? What's the answer going to be? Oh, they don't commute. Oh no. Arithmetic's wrong. We have to start again. So that's actually a problem. Like, it's actually not a huge problem because it's really close. So if I put this all in brackets, you know, we get something, again, my internal floating point brain goes, oh, it's 10 to the minus 16, it's floating point epsilon. It's just one of those things. The problem comes when we try and compound these things. So you do a bunch of calculations, one after the other. These things can grow and get annoying. So it's usually not a big error. This one's fun as well, is like we can add things to things and they don't actually add. That one's actually true. Oh, jeez. So if you're trying to add a little thing to a big thing, you don't actually do anything. I think I've got a little demo of like how to think about that. Okay, how to add floating point numbers. So I said it's like scientific notation. So let's just do it in decimal scientific notation. We've got two numbers, A and B, and they've got some fixed precision in the exponent and the significand. If you're going to add these two together, what you do is you would shift them to the same exponent, go to the big one. So in this case, 10 to the minus 3. That's equivalent to a decimal bit shift. A dex shift. I won't say that. That sounds really bad. Decimal, you would just shift it over two places so they have the same exponent and then add them together. So this kind of gives you the hint about why the little one gets eaten by the big one, because when I shift these guys over with this fixed precision, the 3 and the 4 drop off the back. So then when I add them together, it just disappears. So like if I've got a number that's small enough, when I do this shifting, that's basically hand wavy what happens in the CPU when you add floating point numbers. That's why you get this fun behavior of like, cool, this guy eats this guy. Like, dang it. Again, this is like, please don't use globals, but I just did it here for the notes, for scope. If you keep doing repeated additions and things like this, errors will get big. So this usually will manifest in numerical linear algebra. Talking about that just before the lecture, where I put this one in here because this is every 6 months I get this bug, and thought I should show it to you guys because it's like in my day job, nearly always comes up. I've got an example, pathological example, I'll say, because I just wanted to construct one that's degenerate and bad. If I do, maybe, who knows, lots of stats. So if I do this little quadratic form thing, if I do x dash times x, I'm going to get a matrix. And what would I expect as, who knows enough stuff. What would I expect of the eigenvalues from this matrix for anyone who's done lots of linear algebra? What should be true?
The determinant is 0, right?
Oh, they should all be positive. Yeah, it's rank efficient, but yeah. So what this is like, I'm doing like the normal thing to here would be if I'm doing a covariance matrix, right? Like I'm doing this outer product. covariance matrix on the diagonal, like it should be semi-positive definite. But if you do something like this, if I look at the eigenvalues, you know, there's one at 60 and then there's a whole bunch of little ones, and there's actually like 2 of them that have gone negative on me. So I didn't get this nice thing of like, they're all zeros and there's one that's 60, which is what you would expect from the maths. I've actually got it's actually gone non-semi-positive definite on me. And so if I'm going to use these eigenvalues later on, so like, for example, this should be something like the variance of this thing, right? So if I try and take the square root of the variance to get the standard deviation, what's going to happen? Yeah, I'm going to get imaginary stuff. It's like, this literally, because I'm doing a lot of stuff with statistics and things like covariance matrices, I'm doing machine learning in my day job. Having a thing where I'm expecting it to be semi-positive definite, and because of floating point, it ends up not quite being semi-positive definite anymore, and I have to catch it and fix it, is a huge problem. I think it's just like, that is my literally every 6 months I get this bug in code. Cool. This, we'll talk a little like more later on about, there's a little bit of a demo of like linear algebra functions in Julia. This has big things when you're trying to do matrix solves, like floating point precision is a huge problem in numerical linear algebra. And these things of like, we talked about in the first section about like doing inverse square root, like the reciprocal of the square root and how you calculate that. It's kind of better to calculate that and then multiply rather than divide by the square root. Similar idea carries over to when you're doing numerical linear algebra. It's like most of the time you want to do a factorization where the inverse is nice to calculate for floating point reasons and then multiply by that. It's like, there's all this class of methods called like QR decompositions, Gillespie decompositions. Lots of very smart people have thought about over the years, just fighting these little floating point gremlins and having very clever magical methods for doing it. So much so that basically re-implementing your own numerical linear algebra library is a nightmare and no one wants to do it. So we're all stuck on these old libraries that were written in the 70s. Like BLAS, I talked about that before. Cool. That's probably a reasonable time to stop. Any questions on that? Floating point errors? This will get you. If you're doing simulations, it'll get you. The one that will come up, we'll talk about that next time, is this like this big guy eating the little guy will come up when you do finite difference methods. Because basically, if you think about what's the definition of a derivative, you're trying to do a tiny step, this will come up. Talk about that on Monday. Thank you, everyone.
What's your bit string of 0, 0?
Yeah, I'll just this guy first.